Our next case study is the bromination of acetophenone. In contrast to the examples we've considered in the videos in the first two parts of this series, acetophenone reacts more sluggishly than benzene does. Consequently, the ketone substituent is termed a deactivating group. Deactivation of the ring occurs when a substituent is electron withdrawing rather than electron donating. The withdrawal of electron density from the ring makes it a poor nucleophile, thereby causing EAS reaction to proceed more slowly. In this case, the ketone is conjugated to the ring, so pi electrons from the ring can be delocalized into the carbonyl. This places a positive charge in the ring and clearly illustrates how electron density has been removed. To fully appreciate the meta-directing effect of the ketone, we'll examine the mechanism of the reaction in depth. However, the resonance structures we've drawn do foreshadow the outcome. The ring must use its most nucleophilic positions to attack the electrophile. When we take another glance at the resonance forms, we see that the ortho and para positions are certainly not nucleophilic, since they bear partial positive charges. Therefore, the only position that can be nucleophilic is the meta position. It is extremely important to be clear about the significance of charge. It is not simply having a charge that matters. It is the sign of that charge. On this slide, we see the resonance forms of anisole first and acetophenone second. Anisole was considered in part 2 of this series, and acetophenone is the substrate we are currently using. Notice that both of them have resonance structures that place charges in the ortho and para position, yet their behavior is totally different. So it is not simply that a charge exists at those sites that matters. It is the nature of that charge. For anisole, the first set of resonance structures, the charge is negative. That shows that the ring is electron rich and activated as a nucleophile. It also shows that the ortho and para positions, the sites holding the negative charge, are the most nucleophilic, and they are the sites where EAS is most likely to happen. However, in the resonance forms of acetophenone, we see the exact opposite taking place because the nature of the charge is opposite. When we have a positive charge in the ring is rendered electron poor, which makes it a weak nucleophile. Therefore, the ring is deactivated toward EAS. Additionally, the ortho and para positions are the last sites that we would consider using as nucleophiles because of the positive charges at those sites. And as a result, EAS happens at the meta position. Let's return to the bromination of acetophenone and further rationalize the meta-directing effect of the ketone by drawing the complete reaction mechanism, which begins with Lewis acid-base complex formation. The aromatic ring then attacks the terminal electrophilic bromine atom to form a carbocation intermediate, our sigma complex. Notice that in the meta pathway, the positive charge is never placed adjacent to the ketone in any of the resonance forms. File that away in the back of your mind for just a moment. Meanwhile, let's finish off the mechanism. Loss of a proton restores aromaticity to the ring and gives us the final product. Since the ortho and para pathways are electronically equivalent to one another, let's consider just one of them to illustrate why the ortho and para products are not formed in appreciable amounts during this reaction. If the attack on bromine installs the halogen in the ortho position, the positive charge in the sigma complex resides on the carbon directly adjacent to the ketone. Although this cation has two additional resonance forms, the first one shows significant repulsion between the positive charge of the carbocation and the partial positive charge of the carbonyl carbon. This raises the energy of the resonance hybrid, disfavoring the ortho and electronically equivalent para pathways. In summary, the ketone is both deactivating and meta-directing due to its electron withdrawing nature. This trend holds true in most cases. Most, but not all, deactivating groups direct meta. We'll see a notable exception to this trend in part 5 of this video series. So to recap, when acetophenone is halogenated, the product is meta, and the reaction is more sluggish than that of benzene, so the substrate is deactivated. The next video in this series will continue our discussion of the effect of substituents on EAS reaction. We'll make some generalizations about activating ortho-para directors and deactivating meta-directors.